All right. Here's where we were last time. We've got our fan, we've got our bug clinging it to the... Oh, do we have circles? Have circles. Do we have circles? We have circles. Okay. All right. So the radius of our fan, or the distance of the bug to the center of the fan was? Remember this from last time? That's true, but the actual distance, I think, was 2.6 feet. Is that right? Last class and in the workbook there. So the radius of the distance from the hub to the bug was 2.6 feet. And we were interested in pinpointing, so given an angle, so given some angle, measure, swept counterclockwise from the 3 o'clock position, we were interested in locating the bug, or pinpointing the location of the bug. So for instance, I could just stop this anywhere here. And so what are we going to need, or what did we say our reference was to get a location of the bug? Remember what we said? We gave us some references to get a location. Taz? Okay, so we define what we're going to call the horizontal diameter. The horizontal diameter goes through the fan there horizontally. And how did we use the horizontal diameter to help us with the position? Yeah, so I'm showing in red there the vertical distance of the bug from the horizontal diameter. So given a certain angle that the bug sweeps, angle measure that the bug sweeps, that determines a particular vertical distance, and then as the angle changes, as the measure of the angle changes, so does that vertical distance. And so how do we measure that vertical distance? What do we measure that vertical distance in? What unit of measure? Okay, so we could do feet. All right, so we could measure it in feet. And so that would be vertical distance above the horizontal diameter, and so we could do it in feet, or whatever distance unit that the radius is in. Okay? But we said that's not the only way we could do it, right? So Fuda, how else could we measure this vertical distance above the horizontal diameter? Do you remember? Besides feet. Yes, like inches or centimeters. Okay, yes, so we could do that. But then there was a different way than just like normal distance units. Do you remember what it was? Radians is openness. Radius lengths, right? So instead of using feet or inches or centimeters, we could also measure that in radius lengths. And we said that there was an advantage to that. Do you remember what we said? Why is there an advantage to using radius lengths? Patrick?
It's applicable to any size circle.
Right, so if we measure the number of radius lengths right now, that is, well, now it doesn't matter how big or small the fan is, that number of radius lengths will stay the same. So it's universal, right? It's universal. Whereas the feet, would only work for this particular fan, or this particular distance that the bug is away from the center of the fan. Okay, so let's just do a quick practice here. So I'm just going to let this go here and not even going to look, and I'm just going to hit pause. No, I didn't want there, somewhere else. Okay, so right there. So I want you to, no calculator, I want you to estimate all three things. Estimate the angle, measured in radians, swept counterclockwise from the 3 o'clock position. Estimate the vertical distance above the horizontal diameter in feet, and estimate it in radius lengths. Okay, so try no calculators, no calculations. It's just an exercise of understanding these quantities and taking making a stab at it.
So you just want the vertical distance.
I want three things. I want an estimate of the measure of the angle in radians, swept counterclockwise. I want an estimate of the vertical distance in feet and in radius length. So you're estimating three values. No calculator, no computations. It's just by eyeballing it. Okay, Walter, did you come up with an estimate for the measure of the angle in radius and radians? So starting here, so can you estimate how many radians it is to there? Doesn't have to be perfect. 7 radians to there. He wants around something 7 point something radians. How many radians is a full circle? 6.28, right? Yeah, so every radian is equivalent to 1 radius length of arc length, right? So you want to try again? So it's not going to be more than 6.28. 6.28 is how many radius lengths to get, or about, to get around. So like 4, okay? Maybe 4, 4.5, something like that. So maybe 4, 4.5 radius lengths. Okay, how about the vertical distance above the horizontal diameter in feet? Nadine, in feet, what would you estimate that value right now to be? 2.4. First of all, negative because it's below, right? So this, we're defining this above being positive. So negative 2.4. What do we think? Yeah, maybe like negative 2.5 or 2.55 or something. But yeah, so you got the right idea, right? So maybe this is negative 2.55. Okay, what about in radius lengths? Justin?
In radius lengths,
Would you say the vertical distance above the horizontal diameter in radius lengths is of the bug right now? 4.2 radius lengths. 4.2 radius lengths. What do you think? Alex?
say it's like 0.9.
0.9.
Well, it's got to be
Okay, so then what is it?
negative 0.9.
He sensed negative 0.9 radius lengths. What do you think? Yeah, pretty good. He's saying, so what are we saying? It's like 9/10 of the way down to a full radius. We know full radius length would be at the bottom. So a little bit shy of that. So negative 0.9, negative 0.95 even, right? It's really close to the bottom. Okay. And then we could have that same conversation. So that's just only one aspect of position, right? Vertical distance. The other aspect of the position is? Horizontal distance from a vertical diameter, okay? Yeah.
Sorry, I just have a question for the other.
Yeah, sure.
How did you identify the radius?
I gave it to you, 2.6 feet. Is that what you meant?
No, not the radius. It's the other example that you did. The bug stopped around this part of the area, and then with the horizontal diameter, you said 0.9 radius length, negative 0.95 radius length.
Okay, so back to that example. So the vertical distance above the horizontal diameter in radius lengths. Just a little bit further. Like that?
Okay. How did you get negative?
What do you think it is? So what you're thinking about, how many radius lengths above the horizontal diameter are we? Is the bug?
From what I know, it's radius length is equal to radius, right? Equal to radius.
No, so that's an angle measure. So that's an arc length. So that's angle measure. Now we're just talking about, we can measure this straight up and down. We can use the radius to measure straight up and down how high or low the bug is. Okay? So at the bottom of the circle, how many radius lengths, down here at the very bottom of the circle, how many radius lengths is the bug from the horizontal diameter?
Negative 2.6. No.
Radius lengths.
Radius length.
How many radius lengths?
Negative 1.
Negative 1.
Okay.
You see? So negative 0.9.
Okay.
A little bit, not quite all the way down. You see? Yep. Okay. And so then if we put it together, then if we put both quantities together, we can pinpoint for any angle swept, we can pinpoint the location of the bug. Okay, so we're going to investigate, we're going to go back to the first one, vertical distance above the horizontal diameter. We're going to investigate this covariation in more detail. Okay, so we're going to look at the input of the angle, measure of the angle, swept counterclockwise from 3 o'clock. It has to be that angle. Okay, there's a lot of different ways that we could define angles here. We could say defined from 12 o'clock, defined from 6 o'clock, defined from 4 o'clock. Okay, so we're going to always define it starting at 3 o'clock, and also we could define them as sweeping clockwise. We're always going to define ours as this conventional angle as swept counterclockwise from 3 o'clock. Okay, so the output we're going to look at to start with is our vertical distance above horizontal diameter and we're going to do radius lengths. So if we want to investigate the covariation of these two quantities, what was our process for doing this? We didn't do it that long ago. So we have two quantities that change together. As the angle changes, so does this vertical distance change. What was our process for investigating covariation? Do you remember how we started? Audie?
Investigating if the values themselves vary and not the changes, and then you say that they covary.
Okay. And even before that, how did we get started? So what did we do to ask before we asked those questions? That's right.
We had to define what it meant.
Define what it meant. Like the quantities?
Yeah.
Yeah, so we got our quantities. And what did we do next? Alex?
Wouldn't you define your independent and your dependent?
Okay, we got it. The independent's the input. It's going to be our angle. And then our dependent's going to be the vertical distance. Nina?
Change one at small, consistent increments.
Which one?
The independent one.
Right, so what we're going to do is we're going to take the input, which is our angle, and we're going to change it with small equal increments. Here are the increments we're going to use. Like this. We're going to change it small equal increments. And then we're going to ask these questions that Audie remembered regarding the output. What does the output do as we change the input by these small amounts? So what angle is this? In radians? That's a pi over 2, so then half of that would be? So we're going to go, to get our small amount, we're going to go half of that. So what angle is that right there? Pi eighths, okay? So this is pi eighths. So we're going to go pi eighths at a time, and we're going to investigate what the output does as the input increases by pi eighths radians each time. So this is too, I needed to change this, it's too small. But what that says is, for equal increases in the input, does the output increase or decrease? So we're just asking about the output first. And then the second thing we ask is, do the changes in the output increase or decrease? And to help us with that second question, remember we asked, are the changes becoming more positive, less positive, more negative, less negative? And then from number 2, then we can conclude whether the rate of change is increasing or decreasing. Okay, so here we are in the first quadrant. And I'm going to show over to the right there I got a reference to help. And this should remind you of your web work, okay? So in this first quadrant, as theta increases, does the output, the vertical distance, increase or decrease? Does the vertical distance increase or decrease? In or D? Increases, right? The bug's going up. That vertical distance is increasing, the bug's going up. Okay, what about the changes? The changes, Omar wants decreasing. Do the changes increase or decrease? So here's the first change, and then the next change, and the next change, and the next change. Changes are decreasing, therefore the rate of change is decreasing. So we've got an increasing quantity whose rate of change is decreasing. So we can graph that. So what we're going to do is we're going to set up our input is our angle measure. And all the details are up here, right? I'm not going to write all that stuff out again, but this is the quantity that we're putting on the x-axis. Okay, and then on the what happened? Okay, and so then on our y-axis, here we're going to put this vertical distance. Again, all the details are written above, okay? So angle measure and vertical distance. And so if it's increasing, but the rate is decreasing, then what will that graph look like? So if the quantity is increasing, but the rate is decreasing, because the changes are decreasing, then what will that graph look like? Khan? I thought you... No. What will that look like? Tim? Not sure. If a quantity's so if a graph is increasing, what does that look like? Going up. But if the rate or the changes are decreasing, remember what that's called? Anybody else? Brooke. So we know it's going to be going up, but then the rate is decreasing, or the changes are decreasing. And we called that, she drew with her finger, concave down. There it is. So we're this angle measure, this sweeping counterclockwise, now we're straightening that out and putting it on the x-axis like this, right? We're angle measure now is being quantified, straightening it out this way, and then the vertical distance is just, right, just matches right up, right across here. How high the bug is for a given angle measure this way. Okay, next quadrant. So in the next quadrant, we're going to continue, and your reference point is still over there to the right. So we're going to keep increasing the input by pi over 8 at a time. And we're first going to ask, what about the output, the vertical distance? Does it increase or decrease? Hamid? Decreases. The bug's going down, right? So that vertical distance is decreasing. Okay, so do we have positive then or negative changes, first of all? If it's decreasing, negative changes, right? So here's what the changes look like. The first change is like this, from here to here. And the next change to this point. So here are these negative changes. And watch it in action here. Down a little bit, down more than the first time, down even more. So each time, the negative change is more negative, right? These are getting more negative. So, are those changes increasing or decreasing? What's that? Increasing. She says they're increasing. Anna, do you agree with that? That these changes are increasing. Morgan, do you agree with that? The arrows are getting longer, right? So they must be increasing. Audie?
Well, they're getting more and more negative.
More and more negative.
They're decreasing.
These are decreasing changes. We've got to keep repeating this over and over again, right? So we've been through this maybe 2 or 3 times, but it just doesn't stick easily. It's okay. So it's like the first change was negative 0.1, say. And then the next change right here, negative 0.2. I'm just making these numbers up, okay? It's just something in the ballpark. So say this first change was negative 0.1, then negative 0.2, then negative 0.3, then negative 0.4. Is that list an increasing or decreasing list of numbers? Those are decreasing, getting more negative. So here the changes are decreasing. So the quantity is decreasing and the changes are decreasing too. So what will that look like? We got our first part of the graph here like this. Maybe. So what will the next part look like? So that it's the vertical distance will be decreasing and the rate of change is decreasing. What will that look like? Hamid.
It's going to go down.
Go down.
Increasing changes.
With what?
Decreasing changes.
Decreasing changes. So what will that look like for the graph then? How do we describe that?
Concave down.
Concave down. And here we are at what angle now? What angle are we at? This is right. So we've just made it halfway around the circle. We know that's pi radians. That's our angle, pi. Okay, so now I want you to get a partner. And I'm going to I'll keep repeating. I'm going to keep showing you the bug moving through the third quadrant. You're going to watch the reference points are here, okay? Watch the reference points, and we're going to answer again. What is the vertical distance doing? Is that increasing or decreasing? And then what about changes in the vertical distance, okay? So find a partner, and you're talking through this, okay? So there's going to be 12 or 15 conversations going on. Oh. I don't want to show you that yet. Okay, here we go. Ready? Here we go. Wow, it's touchy. Okay, here we go. See if I can. Having trouble here. There we go. All right, let's see. How about Jared? Talk to me. Third quadrant.
The output is decreasing.
Okay, so first of all, the output. Saying the vertical distance is decreasing. Do we agree with that? Okay, you're off to a good start.
The changes in output are decreasing as well.
So the changes are negative, and you're saying you're getting less negative? Okay, agree with that. You said changes are negative and getting less negative, and so therefore the changes are decreasing or increasing? Just Jared, not.
So the changes are still decreasing.
Changes are decreasing. They're getting less negative. Wow, I think it's because I'm standing at an angle. Okay, so here are those changes. You said they're getting less negative. And so changes that get less negative so those down arrows are getting shorter, right? Those changes. So, increasing changes or decreasing? Anna, why?
Because the amount that they're decreasing is smaller.
Right, right. Yeah, so those are increasing changes. We get the biggest downward change first, and then we get smaller and smaller downward changes or negative changes, which truly actually means that those changes are increasing. And so what about the shape of the graph? So we have a decreasing output with an increasing rate of change. What are we going to have? Decreasing with an increasing rate of change. Shola, what about the shape of the graph then? So it's going to be, starting from here, it's going to be decreasing. The vertical distance will be decreasing, and its rate of change will be increasing. That's increasing. The vertical distance is going to decrease. It's going to go down. There you go. Yeah. So we call that concave up. When the rate of change is increasing, our graph is concave up. And the rate of change is increasing because the changes are getting less negative. Okay, last part. Does it make sense? Agree with that? You guys can talk. So what's going on? All right, so Jonathan, take me through the fourth quadrant here. What about the vertical distance? Increasing or decreasing in the fourth quadrant? The vertical distance.
Oh, it's decreasing.
Increasing. The bug's going up, right? The bug's heading up, so the vertical distance is increasing. What about the changes? Are the changes increasing or decreasing?
Changes are decreasing.
Changes are decreasing. Why?
Because it's becoming
More
more positive.
positive. So when changes become, I agree, when changes become more positive, so we got a little positive change, then we got a slightly bigger positive change, bigger and bigger positive changes. Increasing or decreasing? Increasing or if you got bigger and bigger positive changes, you have increasing changes or decreasing? Bigger and bigger positive changes. That's increasing. It's increasing changes. So the vertical distance is increasing and the changes are increasing, or the rate of change is increasing. What will the shape of the graph be? It'll be heading up, and then how will it be heading up? Or rate of change is increasing. Corey, what do we call that? If the rate of change is increasing, that means the graph is? Just straight line like this? Remember what we called it? Fuda, remember what we called it? Concave up. When the rate of change is increasing, concave up. Okay, so this is the covariation of angle swept counterclockwise from 3 o'clock and vertical distance above the horizontal diameter in radius lengths. Okay, so what's the maximum that we get for the vertical distance? No, the maximum of the vertical distance. What maximum vertical distance do we get? What are we measuring our vertical distance in? In radius lengths, right? So what is the maximum value of our output? 1. And at what angle does that occur? The angle of sweeping pi over 2 radians. So when we sweep pi over 2 radians, that's when the bug gets to the top, and we achieve a vertical distance of 1 radius length up. 1 radius length up. Okay? What's the minimum value in radius lengths of the vertical distance? And that occurs at 3 pi over 2, or 1.5 pi. At the bottom of the circle, right? Okay, so we said that the reason we did this in radius lengths was now this applies to any circle, right? Any circle, doesn't matter how big or small it is. When you get to the top of the circle at pi over 2 radians, no matter what circle you're at, you're 1 radius length above the horizontal diameter. If the circle is 500 miles or 0.05 millimeters, you're still 1 radius length up. Okay, so this setup right here, this input and this output is universal. And as such, that makes it very special, so we give it a special name, this relationship. So if we make a function out of this, our input is theta. We use theta to mean this angle swept counterclockwise, or the measure of the angle swept counterclockwise from 3 o'clock. And then this output of vertical distance above the horizontal diameter and radius lengths, some of you know. What is it called? Sine. Sine of theta. This is not multiplication. This is a function. Sine is a function acting on the input theta. Okay, so it's not sine times theta. Sine is a function that operates on the angle. You give it an angle, it gives you vertical distance above the horizontal diameter in radius lengths. So understanding the sine means understanding the input and output, knowing that very well. Okay, so what if I wanted to measure the output instead? We'll do it in blue. I wanted to measure it in feet. So when it gets to this maximum point up here, say I wanted feet. Well, how many feet would it be up above the 2.6, right? Okay, so I'm like making a new scale here. So at some point it's halfway up, right? Say right about here. How many radius lengths above is it when it's halfway up? 0.5. And how many feet? 3 feet? 1.3. And in feet, what's the minimum I can get? How many feet above is it here? Minus 2.6. So we can use sine then to help us get, for this particular fan, this particular bug on this fan, we can use sine and write a new function so that the output is in feet. And we'll call that g. Okay, I'll call that g theta. So if I want the output in feet, this vertical distance above the horizontal diameter in feet, we can start with sine and say, oh, what do I need to do to sine to get the corresponding number of feet that I am? Piece of cake, right? What will I do? Justin, what do you think? Cosine theta. Khan, what do you think? I want to make a new function that no longer outputs in radius lengths. Now it's going to output in feet. So how can I get feet from number of radius lengths? Right? So I've got number of radius lengths, that's sine theta. How can I easily get the number of feet from that? Cosine theta. Brian, what do you think? Is it cosine theta? How would I get the number of feet if I knew the number of radius lengths? Okay, so what's my rule for g theta? That's right. That's it. So all you do is take that sine, that number of radius lengths, and multiply it by the radius. It'll give you how many feet you are up, right? When you're 1 radius length up, you're 2.6 feet up. When you're half a radius length up, you're 1.3 feet up. It's just 2.6 times radius length. Should make sense. Should make perfect sense. Anybody have a question? Okay, so highlighting again. What is sine theta? Sine theta is about an input quantity and an output quantity. The input quantity is the measure of the angle, so counterclockwise from 3 o'clock. The output of sine, or what is sine itself? Sine is the vertical distance above the horizontal diameter measured in radius lengths, which allows it to be universal for any circle. Then for your specific circle, you have a radius. You're just going to take that radius, or radius. So sine is like the fraction of the radius, right? It's like what fraction of the radius are you up above or down below? And so then to get it in feet, you're just going to multiply by the length of your radius. Alex?
Would it be possible to use, instead of measurements of pi for the input, use degrees again?
Yes. So in terms of the input of sine any angle measure is fine, just as long as you know what you're using and you stay consistent. But the output will always be radius lengths. Yep. Okay. So now we're going to do this again. We'll go faster, and you'll do more of the work. For horizontal distance, can I erase this? Can I erase everything I've written? So now we're going to change the output to horizontal distance right of vertical diameter. Now this is a little trickier because when we do this now, What is our input is the same. It's the measure of the angle. But the output now is a horizontal distance, and that we're taking that horizontal distance and we're going to graph it vertically on the vertical axis. So before, our vertical distance above the horizontal diameter, it just matched right up with our axis here. See that? So it made it really easy. Wherever the height of the bug was, that was the height of our graph, because our y-axis just matched right up with height above vertical diameter. But now we're measuring horizontal distance, and we're mapping that on this vertical axis. So we don't have that nice just association right across like that. So we have to keep track of the values as we do this. So in this first quadrant, so let's write down our, again, this is angle measure. Swept counterclockwise from 3 o'clock. But now we're going to do horizontal distance to the right of the vertical diameter. Just write horizontal distance. Okay, now you guys are going to do the work. So I'm going to, again, you're going to ask, what does the horizontal distance do? Say in the first quadrant. Does it increase or decrease? And from what to what? From what value to what value? And then the changes in horizontal distance. Do those become more or less positive or negative? And therefore, do they increase or decrease, the changes? So first quadrant, get your partner, answer those questions. What does the horizontal distance do? What do the changes in horizontal distance do in the first quadrant? Your reference is up above. Your reference is up above. Okay, so who do we need here? Austin, first quadrant. Tell me about the horizontal distance to the right of the vertical diameter as the bug sweeps the first quadrant. Decreasing. Okay, so from what value to what value is it decreasing, the output? Starting at what value, decreasing to what? He wants from 1 to 0. Agree with that? Yeah, so the horizontal distance starts at 1 radius length to the right, and then it decreases to 0. Good, so now when our angle is 0, we're really going to be starting up here, right? The first point of the graph is not going to be at 0, it's going to be here because our horizontal distance is 1. And then when we get to pi over 2, that horizontal distance will be 0. Okay, what about the changes? Christian?
In the first quadrant,
Yep.
they are decreasing, the output is decreasing.
Okay.
They're getting more negative.
You say the changes are getting more negative. The changes are getting more negative.
So less positive.
Okay, so the changes get more negative. Are those changes increasing or decreasing? More negative.
Decrease.
Decreasing. And what's the shape of the graph then?
I'm not sure the name
That's the name of it. Yep, so it's going to start at 1 where I got the blue dot, and it's going to decrease with a decreasing rate of change. I thought I had it. Let's see. Oh, no, wrong one. This one. Ready? So it's going to decrease to 1, to 0, I'm sorry, with a decreasing rate. With a decreasing rate, or concave down. Okay, so let's see if we can do the rest on the fly. So, Joe, second quadrant. What about the horizontal distance? Is that increasing or decreasing? The horizontal distance? Decreasing. The bug is moving to the left. So therefore, that output quantity is decreasing. What about the changes? Are the changes getting more or less positive or negative? These changes, more or less positive or negative. So there's the first change, second, third, fourth. Do it again. So there's the first change. Is that a negative change or positive? Negative change. Bigger or smaller negative change? These are smaller negative changes. So the changes are getting less negative. So the rate of change is? Decreasing. What do we think? Nadine, increasing or decreasing? What's that? Rate of change is decreasing. The changes are getting less negative, shorter and shorter negative. Those are increasing changes, right? Increasing. This is this very difficult thing to get a hold of. Less and less negative means actually increasing changes. So we have decreasing quantity with increasing changes, which will look like what? So there's the first part. So our horizontal distance decreasing, we're moving to the left, but the changes are increasing. So Patrick, what will that graph look like? Concave up as it heads down. Okay? Third quadrant. Will the horizontal distance increase or decrease? Malin, so in the third quadrant, will the horizontal distance increase or decrease? Increase. Bug is moving to the right. And what about the changes? So here's the first change, second change, third change, fourth change. Increasing changes. So the bug will increase its horizontal distance and increase the changes, or increase the rate of change. So increasing concave up. That was third quadrant, so that was angle of pi to 3 pi halves. Last quadrant. Con, you want to try it? So in this last quadrant, will the horizontal distance increase or decrease? Increase. And the changes. So here's our positive changes. First, second, third, fourth. What's that? Decreasing positive changes. So we've got increasing quantity, the bug's heading right, but the changes are decreasing. So that'll be going up and concave down. All right, so here's another relationship. Again, it works for any circle. It's universal. And as such, this is a very, very special relationship, so we give a special name. So I'll call this one H. So horizontal distance to the right of the vertical diameter, we call that cosine, and cosine is abbreviated COS. Again, it's not multiplication. This is a function, cosine acting on theta. So you give it a theta, you give it an angle, it tells you what the horizontal distance is. That's what cosine means. Cosine is that horizontal distance to the right of the vertical diameter. Okay, what's the maximum horizontal distance we can be in radius lengths to the right of the vertical diameter? Walter, what's the maximum horizontal distance we can be? 1 radius length. And that's at both at 0 here and back when the bug gets back at 2 pi. You get that maximum horizontal distance and radius lengths at the beginning, the very beginning, and the very end of the first rotation. Okay? What's the minimum that you can be? Diana, so what's the very minimum you could be for horizontal distance to the right? -1, and where does that happen? At what angle do you get -1? At pi. So when you're halfway around this, when the bug is halfway around the circle, it's the furthest to the left that that bug could get at pi. Okay, so what's the maximum horizontal distance in feet? So at this 0 and 2 pi, how many feet to the right is it? 2.6 is the most you could do. And then over here at pi, 2.6 to the left. So we got the same setup. If I wanted, say, j of theta to measure now I want the horizontal distance in feet. How could I write a function, j of theta, that would output the horizontal distance no longer in radius lengths, but for this situation, for our bug, for our fan, in feet? Con. That's it. So you just, whatever that number of radius length is, you're just going to multiply by 2.6. So cosine is like the fraction of a radius length, right? So it's always varying between -1 and 1. So it's like, what fraction of a radius length are you from the vertical diameter? And so if you want feet, then you're going to take that fraction of 2.6. You're going to multiply by 2.6. Okay. This is good stuff, really important. Any questions? Okay, so let's go back to our original fan.
One question.
Oh yeah, always right after I erase.
The horizontal distance
Uh-huh.
from the beginning increased, right?
In the first quadrant,
Yeah.
what is the horizontal distance at 0? Right here. This is angle is 0. No, what the horizontal distance from the vertical diameter right now.
From the vertical diameter, it's
Here's the vertical diameter.
1.
Horizontal distance is 1. That's why we started up here. That's why that graph started
Oh my God.
up at the top. And then by the time you get to pi over 2, now what's the horizontal distance?
Now it's 0.
0. So our y coordinate of this graph went from 1 to 0 because we're putting horizontal distance on the vertical axis.
I see.
You see?
It's because I did the whole thing in the horizontal distance. That's why I got a different graph instead of using vertical distance. In this graph, we were doing vertical distance, right?
No, we were graphing the horizontal distance from the vertical diameter.
Oh,
You just
okay.
told me what is at 0, what is the horizontal distance from the vertical diameter?
1.
1.
Yes.
So we're going to graph that on the y-axis. When the angle is 0, it's going to be 1. And then when we get to pi over 2,
It's going to be 0.
0.
Yes.
Yeah, so the horizontal distance was our y-axis.
Okay.
Okay. So going back to this. So let's... So we've got the fan. We're tracking. We've got these two functions that can track. One tracks the horizontal distance, and the other tracks the vertical distance. And so together they give us the location of the bug. Well, what's that just like? So I'm just going to stop this anywhere here. Okay. So here's the location of the bug. Boom, right there. So right now, I want you to estimate the value of sine and the value of cosine. So for this scenario that I'm showing on the screen, I want you to estimate sine and cosine for this situation right here. No calculator, just okay, so yes, in feet or in both. So is it in feet or is it in both? What is the definition of sine? The output of sine. It is always radius lengths. It is always radius lengths. The output of sine will always measure in radius lengths. What's that? The input could be degrees, radians, gradients, but the output will always measure number of radius lengths. Okay, so let's see. What do you think, Taz? So what do you think sine is here?
0.85.
0.85. What do we think?
Negative 0.5.
You want negative. How about that estimation for that sign right there? Yeah, it's anywhere 0.75, 0.85, 0.8, something like that. All right, cosine theta. Tim, what do you think? Can you estimate cosine theta for this scenario right here? So here's where, if you can't see that, here's where this. Oh, wow. Really bad. Gotta fix that. Anyway, so what do you think, Tim? 1. The cosine is 1. What do we think? Here's the edge of the fan. Cosine is 1. Fuda? Negative 0.65. What do you think? Morgan, so 1 has been offered up and negative 0.65. Where did I lose you? Ask, where did I lose you?
I've never received.
What's that?
I've never received.
Okay, so cosine is, it's all about memorizing what that means. This is the number of radius lengths right of vertical diameter. Okay, so here's the bug right here. So we're really asking how many radius lengths are we right there? How many radius lengths? So is it if it's to the left, then it's going to be negative. And so we're really saying what fraction of a radius length is that? Yeah. Yeah, we can't. So we're just estimating. Just 0.6. Just to go with 0.6. We're just doing an estimate. Yes, we're about 0.6 of the way of a radius length. And with sine, we were about 85% or 80% down of a radius length. Okay, so this is really like something else that you've been doing for many years in math, in terms of locating the bug. What is it? Yeah, someone said it. Yeah, this is just like coordinates, right? So what is the x coordinate of the bug? Sine? It's this one, right? It's cosine. So the x coordinate, or that horizontal distance, the x coordinate is cosine theta, measured in radius lengths. And the y coordinate? Sine theta. So this cosine and sine is really just the coordinates of the point on the circle in a unit of radius lengths, in units of radius lengths. All right, so I'll just do one more example here. How about right here? That's not what I want. Gee whiz, what's going on? There we go. That's what I want. All right, so I want you to estimate the coordinates of that point, both in radius lengths and in feet. Both radius lengths and feet. Estimate the coordinates of that point in radius lengths and feet. And then what does sine and cosine have to do with that? What does sine and cosine have to do with that exercise? Estimate. No calculators. You're just looking at the screen and to the nearest tenth. So
Was the radius 2.6?
the radius was 2.6. That's right. Okay, Shola, you're up. So in radius lengths, what do you estimate for the position of the bug? Tell me something. Just sort of ask me a question if you're not sure what's going on. So, an hour of wasted time. Tim, radius lengths.
I got 0.9.
Okay, so let's stop right there. 0.9, why?
Because the full length would be 1, so it's less than 1.
Yeah, so a full radius length x coordinate would be there. And so you're saying it's a little bit less than that. Okay, cool. And then what about y?
I got 0.45.
0 point. Not quite. Here's 1, right?
Oh, sorry,
You want to change it?
yeah. See the 0.3?
Yeah. Is that right? Which both of them are negative? That second one's negative, right? Because you're below instead of above. How are those estimates? Decent? 0.9, negative 0.3. Okay, so then in feet. How many feet? 2.5 or 2.55 or something, and then down maybe 1.9? Not 1.9. It's going to be less than half, right? Half is 1.3. It's going to be less than 1.3, so maybe like 1. Like that. Okay, what does sine and cosine have to do with this? Justin?
Does it have to do with the quadrant that it's in?
It has to do with the quadrant that it's in. Something's more important than this class. Brian, what does sine and cosine have to do with this? Okay, so what does it have to do with these two ordered pairs that we found?
You have the angle which is at, plug it into the sine, you get the radius length or vertical distance.
So which one?
First
The first one. 0.9? That's a sine?
negative.
This one. This is our estimate for sine of theta, negative 0.3. It's how many radius lengths below the vertical diameter we set, or what fraction of a radius length? And what about cosine? Right, so that's our estimate for cosine. Question, audio, or just scratching? Okay. Okay, so understanding sine and cosine is first and foremost about having nailed down what the input and output quantities are. What does it take? What does it receive? And then what does it give? What is it? Okay? So your quiz next week, not today or Thursday, but next week, is going to be exactly this right here. It's going to be writing down those definitions. So let's practice. Okay, so I'm just going to cover this up right now. Forget about this picture right now. In fact, no, just forget about this situation. Next week's quiz is going to be fill out a table like this. What's the definition of the input of sine? You're writing out a sentence. What's the definition of the output and what unit circle coordinate is it? Same with cosine. So practice right now. This is what understanding sine and cosine is about, is knowing this like the back of your hand. Knowing what the input is, knowing what the output is, and what unit circle coordinate it is. So let's practice right now. And you have to be fully specific, all the details, right? Okay, 1 more minute. Okay, Diana, did you get the input of sine? What's the meaning of the input of sine? The vertical distance from the horizontal diameter. Jared, what do you think? Is that the input of sine? What do you think?
I think that's the output.
That's the output. Okay, so we got, output of sine, so what's the input? Okay. Austin, did you get the input of sine? Okay, good. So I'm glad, Anna. Excellent. It's the measure of the angle swept counterclockwise from the 3 o'clock position. That's what we start with. We start with some angle swept, and that gives us a terminal point on the circle, like where the bug was, And then the output. Diana gave us the output of sine. Say it again. Okay, a couple of details missing. Vertical distance, not just from, but above. And then what do we measure it in? In radius lengths. Vertical distance above the horizontal diameter in radius lengths. And so what is that unit circle coordinate? It's the vertical distance above horizontal diameter. That's the y coordinate. That's the y coordinate. Okay, input of cosine. Toss.
Same for sine.
Exactly the same quantity as for sine. It's that same angle. We got to specify. Swept counterclockwise from 3 o'clock. All right, what's the output of cosine? Nina.
It would be the horizontal distance above above the radius. I'm sorry, the diameter,
Which diameter?
the vertical diameter.
No, you can't. So it's vertical distance.
Oh, did I say vertical?
I'm sorry. You said horizontal distance from the.
It's the horizontal distance to the right of the vertical diameter. Sorry, that's what I wanted to say.
Yeah. In radius lengths. In radius lengths. Coordinate. That's the x coordinate. Okay, so this is we're gonna do one more estimation, but next week's quiz, you'll be writing out these definitions because again, understanding sine and cosine means understanding what they take and what they are, right? So it's the output is what they give, what they are. And so you can't really understand sine and cosine and use it in problems without a firm understanding of input and output. Okay, so now that situation up there, I want you to estimate the sine and the cosine for that right there. And I'll try to sketch the circle here. So there's the left side, there's the top of the circle. So sine and cosine. Who's up? Brooke, how about the sine? What would you estimate the sine to be for that picture? 0.8, positive or negative? Negative? Which is it? It's above, right? So it's positive. 0.8, good estimation for the sine. Cosine. Jonathan. Cosine of that angle. So the angle is it's still this angle, right? Starting from 3 o'clock to the bug. So that's the angle. What's cosine of that angle? What's that? Anybody else? Malin. Negative 0.6. Negative 0.5, negative 0.6, something like that. Okay, there is web work for Thursday. Web work for Thursday. Okay, see you then.
I have a question. So, how do you declare the meaning of the radius? Is the distance from center or
The radius, oh yeah, the radius is the distance from the center to the edge, to the circle, at any place.
the radius like 5? How do you explain it? The circle's radius is 5,
Okay.
5 feet. Then it means what?
That's all points that are 5 feet away from a center point. Okay? So, circle with radius 5. It just happens.